Okay, so I'm going to go on a little bit more, and then, again, keeping with this theme of our interest in Earth-like planets, there's a mission in space now called Kepler, which is doing a special type of observational work to try to detect planets in other solar systems, which could possibly be not only Earth-like planets, but in this region we call the habitable zone, which is just the right distance from their sun, like we're just the right distance from our sun. Okay, so the idea of the habitable zone is that you don't want to be too hot and you don't want to be too cold. It's sometimes called the Goldilocks zone, right? So in the case of the Earth, we have other planets that are outside the habitable zone in our solar system, like Venus. Venus is the next planet closer to the sun. It's 70% of our distance from the sun. It's not radically closer to the sun. It's 70% of our distance from the sun. Much, much too hot. The surface temperature is almost 1,000 degrees on the surface of Venus, okay? Clearly not in the habitable zone. You go to the next planet out, Mars, it's 50% farther away from the sun than we are. Just 50% farther away. But as we've seen, it's cold, very cold. So there's this region we call the habitable zone where you basically can have a water cycle, a freeze-thaw cycle. So Kepler's been looking for planets like that, and the way it's been doing that is by looking at the total amount of light that we receive from a distant star. It's not doing images like this. We can't do that. We can't look at another star with any telescope we have now and actually see any kind of a feature like that. Stars are basically just points of light, even in the most powerful telescopes we have, because they're just so far away. But what happens, though, is that when a planet moves in front of that star, from our point of view, there's a little drop in the amount of light that comes through, because it's being obscured by the planet, right? The planet's not bright like a star, it's dark. So if you look at the level of light from this distant star, there's a little tiny drop. It's only about 1/100% or so. Tiny little drop, but Kepler's able to detect that, and it's able to detect a lot of planets because of that. So I just want to focus on two of them here. Very recent discovery is this,
what if there was a helpline for dinner ideas? Helper helpline, we're on our way.
Hang on. Okay, this is 2.5 minutes of talk.
Kepler 10b orbits one of the 150,000 stars that the spacecraft is monitoring between...
All right, so just to start, okay, so I had a longer video that talked about the mission, but it was too long. So I just kind of explained to you how it works. If you're looking for a slight drop in starlight, which represents the passage of this planet in front of the star, that's the discovery technique. So she's talking about the specific one that...
the constellations of Cygnus and Lyra. We aim our mosaic of 42 detectors there, under the Swan's wing, just above the plane of the Milky Way galaxy. The star itself is very similar to our own sun in temperature, mass, and size, but older, with an age of 11.9 billion years, compared to the 4.5 billion years of our own sun. It's a quiet star, slowly spinning, with a weak magnetic field, and few of the sunspots that characterize our own sun. The star is about 560 light years from our solar system and one of the brighter stars that Kepler's monitoring. It was the first we identified as potentially harboring a very small transiting planet. The transits of the planet were first seen in July of 2009.
Okay, sorry, just to make one little point. So Kepler 10 was the 10th planet they looked at. Sorry, not 10th planet, 10th star that they looked at. They have to kind of specifically look at a given star, right? And usually they don't see anything special. They just see the light is just steady. Just completely steady. So there's no little planet moving in front of the star because there's no drop in the starlight, right? So this is just the 10th one they looked at when they started seeing an effect.
560 light years. It occurred to me that when the light from this star began its journey toward Earth, European navigators were crossing the Atlantic Ocean for the first time in search of new horizons. Today we're still exploring, and our crow's nest is a space telescope called Kepler. One day, the oceans we cross will be the galaxy itself. But for now, we imagine the worlds we discover by putting all that we've learned from our observations and analyses into the fingers of artists. Here you see Kepler 10b as a scorched world, orbiting at a distance that's more than 20 times closer to its star than Mercury is to our own sun.
Okay, so it's a rocky planet. It's Earth-like in the sense that it's a small rocky planet, but it ain't in the habitable zone. See, because it's 1/20th the distance. It's much closer to its star than Mercury is, for example, to the sun in our solar system. So this is, it's one of the first discovered planets using this, what's called this transit technique, but it's not in the habitable system. Sorry, interrupting so much. Go. No. upset now, I can't even get the figures.
Daytime temperature is expected to be more than 2,500 degrees Fahrenheit, hotter than lava flows here on Earth. Intense radiation from the star has kept the planet from holding on to an atmosphere, but here we see flecks of silicates and iron that have boiled off a molten surface and are swept away by the stellar radiation, much like a comet's tail when its orbit brings it close to the sun. Many years ago, before Kepler, our team built a robotic telescope at Lick Observatory to learn to do transit photometry. We called it the Vulcan telescope, named after the hypothetical planet that scientists in the 1800s thought might exist between the Sun and Mercury. A planet that might explain the small deviations in Mercury's orbit that were later explained with Einstein's theory of general relativity. Vulcan is the god of fire in Roman mythology, a name befitting of a world so close to the Sun. When I saw the artist's rendering of Kepler 10b for the first time, the thought that immediately came to my mind was that this is our planet Vulcan. We'd come full circle in our quest, and we know that we've only begun to imagine the possibilities.
Okay, so an interesting example of a planet that Kepler has discovered, but better like toasted bread. You go there, that's pretty much the only thing that's going to be on the menu. But there's another world, that was 560 light years away, that particular one. It was just early in the process of discovery. It's not habitable, it's 560 light years away. But here's another one you might have heard of in the Sun, called Gliese 581, which is only about 20 light years away. It is an Earth-type planet, a little more massive than the Earth, and actually is, it turns out, wow. What I really wanted to show.
This is a News in Space newsflash. An exciting discovery has been announced by Swiss, French, and Portuguese astronomers from research made at the European Southern Observatory in Chile. They have announced the existence of the most Earth-like planet ever found, with conditions that could support life. You are looking at an artistic impression of Gliese 581c, one of 3 planets orbiting a red dwarf star located 20.5 light years away in the constellation Libra. Here we see the planetary system. The cool red dwarf star provides less energy to its surrounding planets. Unlike the hot Jupiter-like planet we are passing, 581c resides in the star's habitable zone, where liquid water can exist. Necessary for life on Earth, scientists believe that liquid water is a prerequisite for life elsewhere in the universe. 581c may be rocky or may have liquid water present. Scientists are excited at the prospects of exploring this world. Further out than our Earth-like cousin, we see another planet with a mass 8 times that of Earth. Unlike 581c, this planet lies outside the habitable zone of the red dwarf star. The discovery of Gliese 581c was made by a team of astronomers using the European Southern Observatory's HARP instrument on the 3.6-meter telescope. This super-Earth is in the perfect spot to support life. The estimated surface temperature ranges from 0 to 40 degrees Celsius, or 32 to 104 degrees Fahrenheit. The planet's size and mass were found by measuring the wobble made by its star as the planet moved around it. The light of the star becomes redder as the star moves away from us and more blue as it moves towards us.
Okay, so it's worth noting, we'll talk about that technique. That's completely different than the transit technique I was talking about before. In this case, that little planet doesn't have to move in front of the star and block light. Instead, it actually has a gravitational effect. So I think that's enough on that one. And, okay. What we're talking about Mars, as I mentioned, we see all kinds of interesting terrain on Mars. There's also, there's a lot of evidence for prehistoric ancient water flows on Mars that we'll be talking about. We also see, of course, fossil evidence for life on Earth, and we found what looked like fossils in meteorites that have come from Mars. This created a huge controversy about 15 years ago. Because meteorites were discovered on Earth, which were known to have come from Mars, because basically they had Martian type of gas that was trapped inside themselves. So they were known to be from Mars, and what we saw were things that looked kind of like little microfossils, and people thought this is actual fossil evidence for life having existed on Mars. That did not actually pan out. But what we do see to this day, color's a little weird here, but this is actually a shot of a crater on Mars, a crater wall, where we actually can see water flowing down periodically, seasonally, into the lower part of the crater. So we actually know that there is currently water on Mars, and that we can have water flows. Okay, I already talked about this moon thing. Okay, well, so we're talking, okay, hurricanes, global warming a little bit, because we're interested in meteorology on the Earth, because it's part of the Earth chapter that we're going to cover. So we're going to be talking about that and the increasing intensity of hurricanes and what possible connection that can have. Yes? Yes. The red dwarf star we looked at, I believe, is, that's right. That's right. Oh, right. This is a red dwarf. Well, a red dwarf star actually is a little less massive than our star. So it's not actually ever going to evolve into a star that looks like our sun, because it fundamentally has a lower mass, and so it basically never gets as hot. That's why it's kind of reddish. Red is a lower temperature than yellow hot temperature like the sun has. So the habitable zone is probably pretty much fixed, and it's a little closer in actual kilometers, than the habitable zone is for our star, because our star is hotter. But the thing about red dwarfs that's really interesting is that about something like half the stars in the galaxy happen to be red dwarfs. So if you look at those, as opposed to yellow, happy sun-looking stars, you're going to find a lot more planets because there's just a lot more of those stars. So the goal now is to look at a lot of red dwarfs and see how many planets you can discover, and that's actually working out pretty well so far. The initial focus was on yellow stars, which we thought, oh, that's a solar-type star, we find habitable zone. But there's actually no reason to think that life would only form around solar-type stars, so that's why they're starting to look at red dwarfs as well. So, sorry, remember that. Okay, I'm going to